In this video, I want to talk a little bit about two things. The first thing is determining if our linear regression is actually useful. Is the equation actually showing a linear relationship between our two variables, or is it just from noise? So we need to ask ourselves, well, is this slope here actually important? Remember, when we calculate a linear regression equation, the slope and y-intercept that we get are just sample statistics. So maybe we take a different sample of our variables and we calculate a regression line, and we'll get something that looks a little bit different. Our b1 and our b0 would be different numbers. If we used every point in the population to find a regression equation, then the slope and the y-intercept would be the true ones. So these are population parameters if we used every point in our population, but we usually just use a sample. So just like how x bar is a sample statistic for mu, little b1 is a sample statistic for beta 1 here. This is the Greek letter beta. So our question is, the sample slope that we calculate, is that actually useful for us? So that's kind of our question here. Is this useful? So it turns out that there's a notion of the standard error of our slope as well. Same idea. If you calculated a bunch of regression lines and looked at the standard deviation of those slopes, well, it would give you this formula here, the square root of the sum of squared errors divided by n minus 2 times sxx. The details of why that's true is a little technical, so we're not going to get into it, but know that it can be shown that this is indeed the formula for the standard error of your sample slope, your little b1. And just a little note, this is going to help us in the future. But if there was no linear relationship between points, something like this, if there was no linear relationship, then a regression line, which I'll draw here in green, would have a slope of 0. So b1 would be 0. Because remember, a slope of 0 means it's a completely horizontal line. As x changes, the predicted value of y doesn't change. You're just using the mean. So our question is, well, is the slope that we're calculating, our sample statistic here, is this significantly different from a slope of 0? So what we can do is we can do a hypothesis test to be able to do this. So let's look at that on the next slide. So a hypothesis test for the significance of a linear relationship between our two variables. Well, remember, we want evidence to say there is some sort of significance, so that means that the slope actually isn't 0, so that's going to be our alternative hypothesis. And our null hypothesis is going to be that there is no relationship. So we want evidence that there indeed is a relationship. So our test statistic is just the same as before. It is how many standard errors is our sample slope away from the hypothesized slope. And here, well, our hypothesized slope is 0, so we can just kind of get rid of that. So really our test statistic is b1 over our standard error. And the number of degrees of freedom is n minus 2. Again, that's for technical reasons. Basically, you can think of you need 2 points to be able to define a line, so we have to subtract 2. That's a reasonable explanation of that. So we could conduct the hypothesis test by hand, but I'm going to show you how computers do it, at least how you can read a printout on a computer. You'll probably learn how to do this in lab as well, but I will show you what the printout looks like, and we can point to where it tells me the info that I need. Okay, here is a linear regression, and the two variables that are given. So somebody wants to predict the aroma score of wine. So here's aroma score, and I guess it's from 1 to 10, given the concentration of the element barium. So here is the concentration of barium, and here is the aroma score of a bunch of wines. And in real life, this is kind of more of the size of a data set that you'd see. Could be a little bit bigger, could be a little bit smaller. In fact, could be much bigger. But you could imagine doing a regression equation for this. But this is done in Minitab, so you just press the button and say, basically, do regression, and you get an output that's very similar to this. I kind of chunked it up, but all the pieces are still here. So it tells us our regression equation. So our slope is given here. So our slope is negative 6.042, and our y-intercept is 6.261. It also gives us a rough idea of what the regression line looks like in our data. So you can see our data here is pretty spread out, but in a general negative trend. So you could imagine fitting a line through it. It doesn't look too bad. So I just want to point out a couple of other things here. So it doesn't give you r all of the time, but it does give you r squared. So here's our r squared value, 0.3492. So we can calculate r ourselves from that just by taking the square root and then having the correct sign. And I believe if we do that, we'll get something along the lines of negative 0.59, something like that. So there's our r value there. And that makes sense. We have a negative relationship, and it's not particularly strong. I would call this a middling relationship. So an r of 0.59 looks pretty accurate. And here it says that about 35% of the variation in aroma is explained by the variation in the barium concentration. A couple of other things. This section here, we're not going to get into. It's not particularly useful when we're talking about simple linear regression, just with an x variable and a y variable. So forget about this. And in some sense, forget about this as well. But we have these two values give us this here is our sum of squareds error. And you can see that since here's the sum of squareds and it's the sum of squares error. And below it, we have our sum of squares total, or the other notation for that was SYY. So our printout gives us that as well. But what I kind of want to show you here is it does that hypothesis test for us as well. It gives us a hypothesis test for the constant too, but we don't really care about that as much. We don't care if the constant is actually significant. That just says that the y-intercept isn't 0. We don't really care about that, so we'll ignore that row. But it's the coefficient that goes in front of our variable, BA. We're thinking of BA, that's our x variable. So it gives us our standard error. Here's our standard error. And it calculates our t-value for us. It gives us a t-value of negative 4.33. And it also gives us our p-value. So we can use this to help us determine if there is evidence that there is indeed a linear relationship between the variables. So let's say in our hypothesis test on the last slide, our alpha was 0.01. So our p-value of 0.000, so it's really, really small, is less than 0.01. So that means we accept the alternative hypothesis that there is indeed a significance in the slope, and the null hypothesis that the slope is 0 is rejected. So this tells us evidence about whether our regression is actually doing something. It's not just kind of noise. The slope doesn't come from noise. Let's look at one more example. So here's an engineering example. So it's kind of vague, but there's a dial on some machine, and it measures the energy consumption of that machine. And let's, for now, run this regression blindly. So we calculate some formula. Here's our formula here. So our slope is 0.2159, and our y-intercept is 4.02. And we're asked, well, is this a meaningful regression? So we can run the same hypothesis test that we did, where our null hypothesis is the slope 0. So is there no linear relationship? And the alternative hypothesis is that there is a linear relationship, which means the slope isn't 0. Remember, no linear relationship is just a straight line across. And just eyeballing it without even looking at our test, this line has a slope that's not particularly steep. So we're thinking maybe this is evidence that there is no linear relationship. And we'll talk about how to see that again in 1 second. But let's just look at our data. I'm going to go to the coefficients. If we look down here at machine settings, so here's our coefficient, our slope. So it calculates our p-value of 0.665, and that's pretty big, right? So that's basically saying that for the t-value of negative 0.44 and positive 0.44, remember this is a two-tailed test, since we just care about difference, not direction of difference, the area more extreme than 0.44 standard errors from the mean, all of this together is roughly 66.5%. So it's not if the actual slope was 0, the chances that we'd get a slope that's 0.2159 or more extreme is pretty large. It's 66.5%. So it's very likely to get something more extreme than the slope that we had. So this isn't evidence, kind of at any real possible alpha that you'd look at, but let's say our alpha was 0.05, where our p-value here of 0.665 is obviously greater than alpha, so we do not reject our null hypothesis. So there's no evidence that there's a linear relationship between our two variables of the machine setting, and energy consumption. And quickly looking at our data set here, you can kind of see the pattern of what's going on. It's not that there's no relationship, it's the relationship isn't linear. It looks like energy consumption starts off quite high for low settings, and then around 20, 22, something like that. It comes to some sort of minimum. And then it increases. So this is an example of a data set that has a non-linear relationship. And remember, the regression that we've learned, this linear regression, can only tell you about linear relationships. It can't tell you at all about other types of relationships. So from our test, we know that there's no evidence that the relationship is linear. If there was evidence the relationship was linear, then there'd be evidence that the slope isn't 0. But given our huge p-value, there is not evidence. So that's how to use these tests here. And by the way, just as practice, remember here, there's our SSE. Here is our SST. And here, or maybe I'll use a different color, in fact. Here is our R squared, and they're kind of the really important values for us.